I am Ricardo Ramírez. I am first year PhD student from Universidad de Chile. My advisor is James Jenkins. And I am going to talk about a still working project of searching for the transmission spectrum of LHS1140b. So what is it? What is LHS1140? It's a super-Earth planet in the habitable zone. So to begin with this talk, I want to give an introduction of how this planet was discovered. So to do that, oh, it's not working. Yeah, better. I have to talk about MERT. MERT is a survey that was looking for transit in M stars around all the sky. It consists of two groups of 8 telescopes, small telescopes, that were located in the 2 hemispheres. And they start observing they start discovering many parameters like distance and metallicity of M stars. But also they discover a super-Earth and a rocky planet. And the most important discovery is LHS1140, that is, how I say, a super-Earth in the habitable zone. LHS1140 is an M star. So what that means? It's a fainter star compared to the Sun, and it's relatively close to 12.5 parsecs, and the magnitude is 13 in R. But as M in optics is relatively faint. And these are the measurements that was present in the Nature paper this year, at the beginning of this year, more or less, and that show what the discovery of the planet. That the right is the radial velocities of the star, and the left is the transit. So with these two measurements, we can calculate the mass and the radius of this planet and say that it's a super-Earth. But there are many super-Earth right now. So what makes this more important? Is how I say it's in the habitable zone. The distance that was estimated is a little farther away than the Earth. I don't know if you can see the plot here. The Earth is a blue dot here. But it makes a very good candidate to do transmission spectroscopy. But because what is the next step is to try to study the atmosphere in those objects. So is this planet like a Earth, a super-Earth like this one, or is a mini Neptune? Or if it has an atmosphere at all? Well, something that we can know is the mean density of this planet, that is 12.5. And that is a lot. It's more than iron, is more like the lead. And so in some way we are certain that it's a rocky planet. So the way to analyze the atmosphere is using transmission spectroscopy. So for the people that are not familiar to this is an animation that tries to explain it, that is trying to measure different transit in different bands. So this is a planet transiting a star, and you can measure the transit tip in different bands. And depending on the atmospheric elements that are there, some elements are transparent, another block the light, so you have different transit tips. So in some way, this is another example in optics. For example, you can have elements like hydrogen or sodium, and it's like the size of the planet is changing in function of wavelength. So it's a curious effect, but it's very useful, because at the end what we are measuring is not the atmosphere directly, it's just the transit. So we make a model of these planets, a relative simple model. We use a code that is published, the ExoTransmit, from a paper of Kempton. And this is, again, in the y-axis is the size of the relative size of the planet. with different, and the line are different composition. One is the solar, and you see in the bottom that is flat, there is no atmosphere. And this is an optic, and that is more like a mess, but it is an infrared. So the important thing about here is that we expect that the size of the planet, or relative size of the planet, or the depth of the transit should be different in different bands. So in some way, this is a very low resolution spectrum, just using broadbands. So to do that, we try to look for with all that we can. Really, this planet have a period of more or less 24 days, but it's not visible all the time here from the ground. Really, it's visible once every year. So, and that was last month. So we applied for different telescope, and what we got was GROND, SOFI, and Hawkeye. And we try to observe at the same time in different bands. And then we have to correct by different effects, like air mass, scintillation, even position correlation that were affecting the data. And this is one example of how is the data. And this is one example of GROND in R of one light curve. I don't know if someone can see the transit here. Well, and also at the end of this light curve, you see a little increase of it. I don't know if you see it. That is about the air mass. Anyway, this kind of effect can be corrected, and then you get something like this. So here the scale, I'm going to go back. The scale for what is from 1.2, 1.02, and this is 1.005. So it's a better improvement. And the model of the transit is in red. But it still is not enough. Here is a better sample in I, in the band I in GROND. And here in the continuum we got a dispersion of 1,200 ppm. So it's really good for GROND. And you have to think that GROND is a telescope of a relatively small telescope compared to the SOFI or Hawkeye. So something that also we did is try to model the noise with a Gaussian process and the transit at the same time to try to get the best possible data from this light curve. And I want to show that like the residual of that model is very small, and you see that it's more like white noise. But at the end of the result in GROND is compared with the model is still very inaccurate. We still have to improve in a factor of in one factor the error of the transit. So for the moment, still we cannot rule out any model. But how I say at the beginning, this is still a working process. We are working with the SOFI and Hawkeye that are bigger telescopes. They have a better signal to noise, but they have other effects that still we have to correct. And we hope that we get what we are looking for. And also, the main difference in our basic model from a solar type planet with an atmosphere like a sun or something like Earth, the differences are more clear in infrared. So, and this is my conclusion. And so, how I say that I expect I get a better result in Hawkeye, and also all this work is also aiming to have a good process in a new observatory like WST. So, well,